All right, so it's my big pleasure to introduce Huck Bennett. Huck graduated from NYU and has been working at Northwestern and University of Michigan after that. Huck is an expert in computational geometry, especially in algorithms and lattices. And today, Huck will give a talk at the intersection of two rapidly growing fields, fine-grained complexity and lattice algorithms. Huck?
Yeah, so thanks very much, Sasha, and thanks very much for having me and coming to the talk. So Sasha perfectly summarized sort of my intro slide here. So what I'm going to talk about today is sort of the intersection of two hot areas of research, lattice-based cryptography and fine-grained complexity. So I'm going to start by sort of summarizing each of these fields and sort of saying why they're interesting on their own, and then talking about their intersection, their confluence, the fine-grained complexity of lattice problems, sort of why this is an interesting study and sort of what we did in this area so far. So the motivating application behind sort of this study is the development of quantum secure, so-called post-quantum public key cryptography. So I think probably most of you have seen this before, but sort of the setup in public key cryptography is Alice wants to send a secure message to Bob, even though they've potentially never met before. So Alice doesn't want any eavesdroppers to be able to sort of read this message. So this seems sort of like maybe an impossible task a priori if Alice and Bob have never even met before. But in the late 70s, RSA showed that in fact public key cryptography is possible, and moreover that it's practical. So the RSA scheme is still in widespread use today. So that was until the mid-90s when Peter Shor showed that in fact, if you have sort of a fast enough quantum computer, then it breaks RSA. So RSA is no longer secure. So this motivates the development of quantum secure cryptography. If we're worried about quantum computers being developed. And we should be worried about them being developed. So there's been a tremendous amount of work since Shor's algorithm on developing and building practical quantum computers. So there was a Nobel Prize a few years ago for experimental developments in quantum computing. And all of the big tech companies are working on it, sort of culminating in some sense when Google achieved quantum supremacy, sort of like a milestone in the development of quantum computing about a year ago. So this received widespread press attention. Actually, just last night, as I was preparing these slides, I saw that actually there was just a brand new development from an academic group in China on, sort of building improved experimental quantum computers. So I think we can cross out the coming soon part, and now it's just a matter of sort of when they'll be built and how efficiently and so forth. But anyway, this is clearly a practical problem that we need to address. So we need to develop cryptography that's secure even against quantum computers. So in NIST, the National Institute of Standards and Technology, down the road from you guys in Maryland, has a process ongoing right now for standardizing post-quantum cryptography. And the NSA is also planning a shift or recommending a shift away from traditional crypto to quantum secure crypto. And big tech companies are also aware of this. So even as of a few years ago, Google is testing quantum secure crypto in Chrome. So this is clearly something that's being developed quickly and something that we need to work on. So I'll say more about what fine-grained complexity is in a minute, but so the key idea behind the security of cryptography is that it's based on computational interactability. So the reason that we believe that cryptography is secure is that we believe that certain problems, computational tasks, can't be solved efficiently. So in the context of cryptography, you can think of fine-grained complexity as corresponding to key size. So cryptosystems are typically parameterized by a key size where smaller keys allow for faster encryption and decryption algorithms and lower communication costs, and larger keys ensure stronger security. So ideally, what you want is a crypto system which uses as small of keys as possible, so it's like as efficient as possible while still remaining highly secure. And so you can think of fine-grained complexity as a tool set for sort of understanding this trade-off in a non-ad hoc way. And this is an important study. So for example, RSA with the original proposed key size was broken after about 20 years. So which is not something that we want to have happen in the future. Okay, so a bit more about fine-grained complexity. So how do we show computational intractability in computer science? So generally, there's sort of a two-step process. So you take some well-understood problem, say the SAT problem. So here's 3SAT, where the goal is to find a binary assignment to n variables in a formula of this form. And then you assume something about the intractability of a problem like this. So for example, you can assume a standard starting point is you assume that p is not equal to np, which is equivalent to saying that 3SAT has no polynomial time algorithm. So step one, find this sort of well understood problem and make a reasonable assumption about its complexity. Sort of the real work you generally have to do is you have to give a reduction. So intractability is based on reductions. We take sort of a well understood starting problem and reduce it to some other problem. And then that lets you conclude something, you can show such a reduction about the intractability of the latter problem. So this is sort of how traditional complexity works, and sort of it lets you carve up the landscape of NP into sort of hard NP complete problems and sort of efficient problems, ones that are in P. And we sort of think of this as characterizing which problems in NP are hard and which are easy. But sort of the idea behind fine-grained complexity is we want to take like a closer look at this. Sort of this is like a very coarse representation of what's hard and what's easy, and especially for problems related to crypto, but also lots of other things. We really want a better sense of exactly how hard certain problems are. So using tools from fine-grained complexity can actually show much more precise lower bounds on the runtimes of a bunch of problems. And actually sort of the runtimes shown here are actually more or less tight, both in terms of algorithms, there are algorithms running in that time for these problems, and sort of these lower bounds are tight, assuming certain conjectures in fine-grained complexity. So how does fine-grained complexity work? So usually you start with some other analogous hardness assumption to p not equal to np about the complexity of say SAT, but usually this will be a stronger assumption than p is not equal to np. There's the exponential time hypothesis, which says that 3SAT takes not just non-polynomial time, but actually exponential time, like maybe 1.01 to the n time or something like that. And the strong exponential time hypothesis, which says that KSAT, or sort of there are k variables in each of these clauses, and not just 3, takes essentially 2 to the n time for large enough k. So which is just saying that brute force is basically optimal. You can always check all 2 to the n assignments to x1 up to xn and solve SAT that way. So you sort of start with these stronger assumptions. But really the more interesting part, sort of the hallmark of fine-grained complexity, is an emphasis on very efficient reductions. So before we were satisfied to have polynomial time reductions between problems, but here we want to focus on very efficient reductions, which will often be linear. Like we want to map we want like linear time reductions where you map n to some like order n or even n to n, something like that. So sort of just like we teach students that quadratic time sorting algorithms are bad and n log n time algorithms are much better. So we wouldn't be satisfied in practice with a quadratic time algorithm when a much faster one exists. Sort of here we want to say that polynomial time reductions aren't good enough. We really want to focus on highly efficient reductions when we can. And that by doing so, by using such very efficient reductions, we'll be able to conclude much stronger hardness about problems that we're reducing to. So it's a bit of the intro material. So just please stop me with questions at any point. This would be kind of a good time just about what I've said so far. Okay. So sort of just pivoting back to crypto for a second. So how do we actually build post-quantum cryptography? So the idea is going to be to use so-called objects called lattices. So what's a lattice? So a lattice is a set of all integer linear combinations of some linearly independent vectors b1 up to bn. So here's a picture of a lattice. So we have which is this regular grid of points in space. So these black dots, which you can think of as running off into infinity, are our lattice points. So in here we have, so here's our bases, B1 and B2, and we get the lattice generated by them by taking all integer linear combinations. So for example, we have like 2B1, 3B1. My pen is not working so well here. I think it's running out of battery, but B1 plus B2 is the one I was writing under here, and minus B1 and so forth. So we get all integer linear combinations of B1 and B2 in this way. Okay, so that's a lattice. And we can build crypto based on lattice problems. So we'll get secure cryptography by assuming that certain lattice problems are hard and hopefully proving that they're hard. So, and one of these problems, one that I'll talk about today, is called the closest vector problem. So this is a computational problem on lattices. So as input, you get three things. You get a basis for the lattice along with some additional target point t, so that's shown in red here, and some distance threshold r. So, and the goal of the closest vector problem is simply to decide whether there exists a lattice point within distance r of t. So here the question is, so again, we have the same basis B1 and B2 as in the previous slide, same lattice, but we want to decide whether there's a lattice point lying inside this blue circle or not. And if we flip back to looking at the whole lattice again, we'll see that indeed there is, that this point 2B1 does lie inside this blue circle, so it's within distance r of t. So this is a yes instance of the closest vector problem. Okay, so and the security of real-world lattice-based crypto is based on sort of understanding the precise runtimes, optimal runtimes of algorithms for closely related lattice problems. So generally, they're analyzed in terms of the optimal runtime for algorithms for a close cousin of the closest vector problem called the shortest vector problem. So this is actually an easier problem than the closest vector problem in a precise sense, meaning that if you have an algorithm for the closest vector problem with a given runtime, then it automatically translates to one for the shortest vector problem with essentially the same runtime.
Huck, can I ask a question?
Yes, please.
Are you going to come back to the closest vector later, or?
I am, yeah.
Okay.
This is just motivating sort of why this will be interesting for or a bit more context for practical.
All right, I'll defer my question then.
Okay, no, that's yeah, but please feel free to ask. Right. So here are three sort of real-world lattice-based crypto systems. So which are all, so the first two are two of the four finalists in this sort of standardization process, and the third is an alternate. So most of the sort of leading contenders for in this process are based on lattices, including these three. And these all sort of make roughly the same estimates for what the value of this CSVP is. So that it's somewhere between 0.2 and 0.3, even if you use quantum computers. And so these estimates are basically based on what we know from the fastest algorithms in a particular widely used paradigm called sieving for attacking lattice problems, but a priori, there's no reason to believe that sieving algorithms are optimal, and maybe they're not. So in particular, if you could show that this value CSVP was like somewhat smaller, like say 0.05 instead of 0.2, then it would break all of these crypto systems, which one of which will likely be standardized shortly to replace RSA. So how do we ensure that such lattice-based crypto systems are secure? So like, how can we try to argue that maybe this value CSVP is in fact somewhat large? So what we want to do is analyze the fine-grained complexity of lattice problems.
Do we expect any quantum speed up like whatsoever for these lattice problems, or none at all, or just a not very big one?
Yeah, I think not very big one is sort of the right answer. So I mean, basically, so here you can see that there are slightly different values for in the classical.
I see. Yeah, I missed that. Okay.
Huge gap. And basically where that comes from is like you can apply Grover search to some chunk of a lattice algorithm. So there's some like a lot of the way these things work is you kind of need to enumerate all things in a big list, and you can speed that up quadratically using a quantum computer. But it isn't as simple as just take the square root of the runtime for the, you know, whatever you get classically. Even it's a bit more subtle than that. But yeah, I don't think, definitely we don't expect there to be super polynomial speed ups in quantum computers.
Huck, and the values of CSVP that you provide here, they're for heuristic algorithms, right? Without provable guarantees.
Yeah, absolutely. So that's important. So these are for heuristics. So this is like in practice, like these are kind of worst case estimates. So like the best we know, the best upper bounds we know, I'll talk a bit more about this in a bit, is much sort of worse than this. So like CSVP of about 1 is a provable upper bound.
What is paranoid, by the way? Is it like the best case for quantum, or what is that?
Well, it's sort of like the limit of like the best you could possibly hope for using this class of sieving algorithms for like, even if everything like in a perfect world, I think that actually relies on unproven mathematical conjectures to get something that's that fast. So, yeah, but I mean, the point, even so, like in some sense, you know, I mean, people like, I gave a version of this talk to a lattice crowd, and I feel like I think I got stuck on an analogous slide for about 10 minutes where people were arguing about exactly, you know, what values to use here. But just sort of the moral for this talk is, you know, these values are all kind of, you know, roughly in the same range. And if it turned out that CSVP was a lot lower, then it would cause big problems. Anything else, or it's good? Okay. Right. So how do we ensure that, you know, how do we reason about this, how that these crypto systems are secure? So we want to analyze the fine-grained complexity of lattice problems. So going back to the closest vector problem, which will sort of be the focus of this talk, there's been a long line of work on studying the time complexity of CVP. So in the early 80s, Van and Boas proved that this problem is NP hard. In the late 80s, Kanan gave sort of the first non-trivial upper bound for the problem, which was subsequently improved. And sort of as folklore at some point, proof of this actually also appears in our work. There's people realize that sort of assuming the exponential time hypothesis, this problem takes exponential time, but maybe just like 1.0001 to the n time. It's really not clear what the C is. And then there's more work on getting sort of faster algorithms for the problem, culminating in a 2 to the n time algorithm, Baggerwald-Dadouche and Stevens-Davidowitz from 2015. So unlike for SAT, this 2 to the n time algorithm is highly non-trivial and is the culmination of a long line of work. Sort of a priori, it's not even obvious that this problem is decidable because you would need to sort of iterate over all of the integer vectors, everything in Zn. But it is, and in fact, it can be solved in 2 to the n time. But this still sort of left a gap in our knowledge. it's unclear sort of exactly what the runtime of this problem is, the optimal runtime of algorithms for this problem. And that's what we tried to address. So in work from a few years ago with Sasha and Noah Stevens-Davidowitz, we showed that this 2 to the n time algorithm is essentially optimal, albeit with a caveat, which I'll mention more about in a bit. But still, we came close, sort of, we morally settled in some sense the time complexity of CVP, the closest vector problem, and thereby ruled out a class of attacks on lattice-based crypto systems. And in follow-up work, which is actually going to appear at a conference in 2021, we showed that even sort of for what seemed like a priori easier problems, or for sort of approximate versions of SVP, or even data structure versions where you're allowed to pre-process the lattice basis ahead of time before you see the target point. So you get to spend as much time as you want sort of pre-processing the lattice ahead of seeing the target point. These problems still take like 1.99 to the n time.
So how,
this work, we also sort of explain and remove part of the caveat. Again, we remove part of it and sort of explain why we had trouble removing the rest.
Huck, I think Nitin has a question.
Oh, sure.
I have a question that might be trivial. I'm completely new to these kinds of hard problems. So does the complexity somehow depend on the choice of the basis, or is it just some, I mean, how, there must be easier versions of this problem, right?
Well, so let's see. So in the, so what we want is, in terms of algorithms, what we want to consider is sort of, even if we're given like a bad basis. So certainly one of the things that makes lattice problems hard is you might get a bad basis as input. So it's like a bad representation of the lattice. But still, the 2 to the n time algorithm mentioned in this slide works whatever basis you get as input. And sort of on the flip side, one way of interpreting, actually, it's a very appropriate question for this slide, is sort of the data structure version of CVP. So what this is saying is, even if you get the world's best basis, the world's best representation of the lattice, and you're like ahead of time, and then you get the target point, the problem still is really, really hard. It still takes about 2 to the n time.
I see. Thank you.
Yeah, for sure. So that's actually it's a good question for this slide too. Okay. So what I'll do now is I'll sketch a bit about just how we showed this hardness. And of course, the idea is to use a reduction. So just a reminder from before. So the idea will be to reduce KSAT, a KSAT instance on n variables, to a CVP instance of rank n. So the rank of a CVP instance is just the number of basis vectors in the instance. So B1 up to Bn will generate the lattice. So, and I bolded the n's in each case, and I emphasize again that it's really important here that our mapping n to n and not n to even like 2n or 3n or something like that. We really want to map n variables to a rank n instance. If we can do this, this will prove that CVP requires essentially 2 to the n time, assuming the strong exponential time hypothesis. And so the idea behind the reduction will be that we'll consider a binary combination of basis vectors, which will correspond to an assignment to the variables of phi. And combinations corresponding to satisfying assignments to phi will be sort of closer to the target vector, and ones that are falsifying will be farther from the target vector. So before seeing the reduction in more detail, it'll be interesting, actually, sort of the key idea is captured by what a priori might seem like kind of a simple or even trivial exercise. So we want to reduce 2SAT, not just KSAT, but 2SAT, which is actually an easy problem to CVP. and actually even just a single clause, two-sat clause. So the key idea behind what we're going to do is actually captured in this picture. So on the left, we have a two-sat clause, x1 or x2. And on the right, we have sort of zoomed in on all binary combinations of some basis vectors of a lattice and some target. So, and I'll explain more about what this picture means in a second. So basically, given such a clause C, like x1 or x2, what we want to do is we want to find v1, v2, and t star such that if we have a satisfying assignment to C, we satisfy x1 or x2, then the corresponding binary combination of v1 and v2 will be at unit distance to t star. And if the assignment falsifies C, then the same combination will be a distance like 1 plus epsilon, some distance strictly greater than 1 to t star. So you can see here there are three ways of satisfying x1 or x2 by setting either one or both of the variables to 1. And if we take the corresponding combination of v1 and v2, either v1, v2, or v1 plus v2, all of those vectors are at unit distance to t star. But the zero vector, which corresponds to setting both x1 and x2 to be false, is at strictly greater distance to t star. So this is sort of the key correspondence here between sort of this Boolean circuit problem and this geometric problem. Okay, so what I want to do now is show how we can actually take the idea in the previous slide and use it to get a reduction from max 2-sat to CVP. So max 2-sat is the problem where you want to solve, sort of satisfy as many 2-sat clauses as possible. Maybe not all of them necessarily, but as many as possible. And this is actually an NP hard problem, and in some certain precise sense, it's like roughly as hard as KSAT, but not in a super fine-grained way. But this will sort of give the idea behind our general reduction. So the idea is we're going to use sort of the geometric gadget in the previous slide over and over again. We're going to use it once per clause. So that sort of works for reducing a single 2 clause to CVP, but we're going to use that once per clause. So say we have some 2-sat formula as input. What we want to do is we want to output a CVP instance with a target, which is sort of close to the lattice generated by B within distance R. If we can say satisfy a lot of these clauses, and where T is farther than R from the lattice generated by B otherwise. So here's what we're going to do. So we're going to output a basis B and some target T. And the basis is going to be indexed by n columns, so indexed by the n variables in our input 2-sat instance. And it'll have m rows indexed by the m clauses of the 2-sat instance. And what we're going to do is, if variable ij appears in clause j, so if variable xi appears in clause cj, then we're going to put either v1 or v2 or minus v1 or minus v2 in the corresponding entry in B. So if the variable appears unnegated, we're going to put either v1 or v2, and if the variable appears negated, we'll put minus v1 or minus v2. So taking care that we use each of v1 and v2 once per row. Okay, so here's this gadget from the previous slide. So this is a reminder. So we're just using the same v1 and v2 over and over again, once per row here. And the idea is, if we think of an assignment y, or like this Boolean vector y, which we can interpret either as an assignment to the variables of our 2-sat formula or as a binary combination of basis vectors, we're going to sort of analyze the contribution of each clause C1 up to Cn to sort of the total distance between this lattice vector B times Y and T. And you can check that sort of if Y satisfies a given clause, then that the sort of row corresponding to that clause will contribute 1 to this distance, and otherwise it'll contribute some amount more, sort of 1 plus epsilon. And because of this lets us sort of measure how many clauses were satisfied by a given assignment to the variables x1 up to xn. So if we could satisfy or sort of solve this CVP instance, like sort of find a closest vector to B, then it would let us sort of tell like the optimal number of clauses that we could satisfy in the input max2 sat instance. So there's sort of one issue here, which turns out to be a minor issue, which is that sort of here we're thinking about combinations of the basis vectors, which are Boolean or binary. So we're just thinking about 0-1 combinations, but of course the lattice generated by B consists of all integer combinations of these vectors. So we sort of need to handle non-binary combinations of basis vectors as well, but this turns out not to be much of a problem. So this is probably the most technical slide in the talk. If anyone has questions, this is another good time to ask. So you can just sort of going back to how this basis is constructed. So you can see here, like here in the first clause, I have x1 and x3. So I've put v1 in the c1 x1 entry and v2 in the c1 x3 entry. So in the second clause, I have x2 and not xn. I really wish the pen weren't dying, but again, so here I put v1 unnegated in the c2 x2 entry and -2 v2 in the c2 xn entry. And so forth. Okay, so great, but sort of to conclude, the hardness we wanted for CVP, it wasn't enough to map 2SAT or even max 2SAT to CVP. What we really wanted to do was to map KSAT to CVP. So sort of the solution to doing so is to use sort of a generalization of the geometric gadget that I showed you before. So this geometric gadget, sort of in the lower right corner, you can call a 2 isolating parallel pipette. So it's a name for this gadget. But what we want to do is we want to sort of come up with a gadget where you have k VIs, so V1 up to VK, and you satisfy sort of analogous conditions. So what I'm going to say is that if you have a non-zero combination of the VIs, then it'll be at unit distance to T star, and otherwise you'll be strictly farther away. And so this key correspondence that we saw before will then still hold, meaning that sort of each k clause, like if you look at the OR of k Boolean variables, then there are 2 to the k minus 1 satisfying assignments, ways of making that evaluate to true, and only 1 falsifying assignment. So the only way to unsatisfy or falsify the assignment is you set all of the variables to be false. And similarly, a k isolating parallel pipette has 2 to the k minus 1 close vertices, so that's all non-zero y's here, and 1 distant vertex, which corresponds to taking all of the setting y up here to be 0. So in this second, in this second case. So the reduction works in a very similar way to what I already showed you. And really sort of the technical crux of our work is constructing these geometric gadgets for k greater than or equal to 2, or strictly greater than 2. So to do so, we use a bunch of cool math, including techniques from combinatorics, linear algebra, and analysis. But the caveat to our result is that sort of with respect to the Euclidean norm, which is what we typically sort of the most common way of measuring distances, these gadgets actually don't even exist for k greater than 2. So this reduction fails. So a more precise statement of our result, what we showed was that there's sort of no 1.99 to the n time algorithm for a CVP in all LP norms of a particular form. So I'll say in just a second what LP norms are, but there's sort of a different way of measuring distance than sort of the most common way, but also appear in a lot of applications. So sort of the caveat to our result is there's a bit of a mismatch between the way we're measuring distance in the fastest known algorithm and the way that we're measuring distance in our lower bound, but still morally very, very similar. Okay. So what I'm going to tell you about now is actually, so briefly talk about showing hardness of actually an easier problem. So a variant of the closest vector problem where you're sort of promised something about the input, namely where you're promised that the target vector is somehow very close to a lattice point. And this is actually a problem which is very close, sort of especially close to the problems used in lattice-based cryptography. So, but to start off, I'll define what LP norms are. So this is just like a different way of measuring distance. So the LP norm for finite p of a vector is just the sum of pth powers of the coordinates of the vector raised to the 1 over p power. And for so L infinity, when p equals infinity, it's the maximum of the coordinates in the vector. And the standard Euclidean norm corresponds to p equals 2. So in order to sort of define this problem, BDD, a bit more formally, I need a bit of notation. So measure the distance between a target vector and the lattice, just as the distance between the target vector and the closest lattice vector. And again, we're going to use these subscript p's throughout to denote that we're measuring distances in the LP norm. So the input to the bounded distance decoding problem, similar to in CVP as we saw before, you just get a basis and a target vector. And the goal is just going to be to output a closest lattice vector. So actually, as I've defined it here, this is the search version of the closest vector problem. What I've written so far is exactly the search version of the closest vector problem. So instead of trying to decide whether t lies within some distance of the lattice or not, I'm just saying like the goal of the problem is I give you a basis and a target vector, and I want you to give me back out a closest lattice vector. So the BDD promise is going to be that somehow the distance between the target vector and the lattice is quite low. So in fact, it's going to be within an alpha factor of the minimum distance of the lattice, the minimum distance of the lattice being the minimum distance between two lattice points. So it can visualize this again. So here's sort of the input to our BDD instance is the same familiar basis and target vector. But now I'm promising you that the closest lattice vector actually lies within this circle. So there's no notion of, we're not trying to decide whether there's a lattice vector within this circle or not. I'm promising you that there is a lattice vector inside this circle, and I'm asking you to find it. So here X is the vector inside this circle, and I'm just asking you, the goal of the problem is just to find X and return it. So when alpha is strictly less than a half here, the closed lattice vector will be unique. There will be just one lattice vector, but the problem is well defined and interesting for all values of alpha. So maybe one more quick remark on this. So as alpha, for smaller alpha, this BDD promise is stronger. And so the problem is easier. And hence, if we can show hardness for it, then we've obtained something stronger. But even if we sort of have this promise at all, then we're already considering an easier problem than CVP, which corresponds to the sort of analogous problem, but without this bullet pointed BDD promise. So basically anything we can show in terms of hardness about this problem will be something actually stronger than what we've shown about CVP on its own. And so in recent work, we sort of looked at the fine-grained hardness, fine-grained complexity of BDD sort of as P changes. So with a focus on what happens when we vary the notion of distance we're working with. And in recent work with Pikert, we showed that actually sort of first off, regardless of what notion of distance you're working with, including the important case of P equals 2, we get that BDD with some value of alpha requires 2 to the omega n time. So where we can pick alpha. So again, we want to get a strong statement. We want to pick alpha as small as possible. And we show that if we pick any alpha greater than some quantity alpha p star, which is plotted here, then we get such hardness. And assuming sort of the strong exponential time hypothesis, we get some sort of trade-off between our BDD guarantee and the runtime of the fastest possible algorithms.
What's the horizontal axis here?
So there's no, the horizontal axis is P, the LP norm that we're working in. The red line is not actually the horizontal. Yeah, so the red line corresponds to unique decoding, which is sort of a barrier for known techniques. But yeah, and the x-axis is P, the notion of distance we're working in. So I think they're these sort of, unfortunately, they're kind of small in the plot, but so this is a plot of alpha as a function of P.
So can you give some info for many distance problems, right? The norm doesn't matter as much. Here it seems to matter quite a bit, actually.
So it doesn't matter when did you say?
I mean, actually what I'm really asking is, can you give an intuition on why the P matters so much here? I mean, there's a significant difference, right?
Yeah, there is. I mean, maybe I'll say something about it, and I'll say something about it in just a second, actually, which might partially answer your question. But yeah, actually, the P plays a huge role here. That's right. Yeah,
but what I was saying earlier was that there are problems that I have worked on in a very different context, where the norm doesn't matter much at all, just because of the norm equivalence. But here, it seems to make a big difference.
I'm curious. Yeah, I'm curious about the problems. I mean, even in other geometric problems like nearest neighbor search or kind of big data problems in high dimensional geometry, often the norm does matter quite a bit.
We can talk later. Yeah.
No, but I'd be curious to discuss that. I mean, certainly for lattice problems, it does. I mean, it also, just as one other comment, it depends on kind of how fine-grained a notion of hardness or or algorithms you care about.
Actually, yeah, maybe I should correct myself. So when I say it doesn't matter, it's not so much about computational complexity. I'm thinking of more about, can the problem be solved at all? More about solvability in distributed computing setting. So we may be talking about apples and oranges here.
I see. Yeah, I mean, that's interesting. So if there's like a dichotomy between what you can solve at all or not. So here we're interested really in not just understanding whether we can solve it or not, but really, pinning down precisely how fast we can solve these problems.
Right. Okay.
I'd be very interested to hear more about that.
Yeah.
Okay. Good. So it looks like I have about 15 minutes left. So yeah, I'm pretty close. I just want to say sort of one note about so I'll say something technical, just sort of about how we go about showing this hardness, and then conclude. So what we're going to do again to show sort of the way that we showed hardness for BDD, we're all sort of a sketch here, is a reduction from CVP, which we saw before, to BDD, which is like CVP with a promise. So to do this, I'm actually going to define a slight variant of CVP called binary CVP, where, so again, given a basis and a target as input, and here, so I'm defining a search problem. So here, I'm guaranteeing you that there's some close binary combination of basis vectors. So that's the binary part. So not just some close combination of vectors, but a close binary combination of vectors. And I'm asking you to find that combination. So this is actually very close to what we saw already. This is actually really just, this is sort of a harder variant of what we already saw, the version of CVP that we already saw. So this is like more or less just the search version of what we already saw, but with this sort of added binary constraint. But that actually just kind of follows immediately from the proofs that we saw. So this previous work that I mentioned and showed you actually already showed hardness of this variant of the closest vector problem. Right. So what I'll do just is I'll sort of show you how to reduce binary CVP in the L infinity norm to bounded distance decoding infinity a half. The reduction is not too bad. Here it is. So I'll try to write some stuff, but I might have to say it out loud if my pen isn't working. So what's the reduction going to be? So again, define these two things as search problems. So what I need to check first off is that B prime T prime is in fact a valid instance of BDD infinity a half. So that would be the first step. But assuming it is, what I'm going to say is that what we would do is we would sort of use like sort of to show such a reduction. What we would do is we would show how to use our BDD infinity a half oracle to solve just run that on this output instance and somehow obtain our solution for binary CVP. So the way we would do it just it would be simple. If we have this oracle for BDD infinity a half, we just call it on B prime T prime. We get some output, some close vector, some B prime X. And what we would do is we would just recover X from that, which I'm claiming would necessarily be binary, and output that as our output to binary CVP. So let me just say, let's see, something about why this reduction makes sense. So what do we want to check? So we're going to check that, okay, I think we're out of luck. So the minimum distance of this lattice is, the first thing I want to say is that it's at least 1. So I should explain this notation. What I've done is I've basically stacked the input basis on top of IN, which is the identity matrix, the n by n identity matrix, and stacked the corresponding target vector on top of the all ones vector. And I've also added a few halves in for scaling. But because of the identity matrix in B prime, no matter what non-zero combination of the basis vectors of B prime I take, I'm going to get a lattice vector which has norm, L infinity norm at least 1. Sort of on the flip side, because I'm promised that there's some combination X, binary combination of basis vectors such that the distance between Bx and T is at most 1, I'm guaranteed that sort of with that, taking that X in the first coordinates, I'll be at distance a half from T. And also, as it turns out, because that's a binary combination, I'll be a distance 1/2 in the lower coordinates as well. So basically, everything I said just proved to you that, in fact, what I've output here is a well-formed BDD infinity 1/2 instance. And again, so the way that this reduction works is, so I have this instance, and now I call my BDD infinity 1/2 sort of subroutine for solving this. I get back some vector, so I'm just which is a closest vector to t prime. And I'm going to argue that vector has to be binary, and that just follows because any a binary combination of basis vectors, and that just follows because sort of any other combination would be you can just tell that from the lower coordinates would be strictly farther away from t prime than what you can get with a binary combination. So I was hoping to write more of that out, but technical issues happen. Anyway, but from this reduction can conclude already that again, there's like no 1.99 to the n time algorithm for BDD infinity 1/2, assuming the strong exponential time hypothesis. So that theorem just follows from this work above that I was mentioning earlier about the complexity of CVP, and then this reduction, this simple reduction. So this is a good sort of sketch. The general reduction is substantially more complicated for finite p, but this sort of gives a beginning flavor for the intuition of what we're trying to do in that case as well. And so the best values that we can get for this reduction, again, remember that to show the best hardness possible, we want to show hardness for the smallest alpha possible. So the way that we get sort of the values of alpha p star, which are essentially the best values of alpha, the smallest values for which we can get some good fine-grained hardness, these actually come from a geometric quantity, which are essentially sort of they're related to the number of integer points in Zn that are in some LP ball around the origin. So this notation BP0 blah 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 is, so this is an LP ball centered around the origin of the radius 1 over alpha times n to the 1 over p pth root of n divided by 2. And just one note, so this might look really weird, but just a note on where the pth root of n over 2 is coming from. So that's the distance in the LP norm between the all halves vector and all vectors in the Boolean hypercube, just of all binary vectors, 0, 1 vectors. So just like sort of the high level message here, I think, which is really cool, is that there's an intimate connection between geometry, lattice geometry, and lattice complexity results. In fact, a lot of sort of, before it was the isolating parallel pipeheads, those gadgets that I showed you that we used in our hardness of CVP proof, and here it's something a bit else. But basically, there's this beautiful connection between geometric ideas in lattices and sort of converting them, geometric results into hardness proofs. And in fact, a lot of the time, just sort of proving something geometric or constructing a geometric gadget is what you really need to get some hardness for a lattice problem. Okay, so yeah.
Do the known upper bounds and known algorithms for BDD significantly depend on alpha?
Yes, but I think they're like and they do, and I think so even in a fine-grained way, but there's there are a few like important things. Like for algorithms, it matters a lot whether alpha is greater than or less than 1/2. So meaning whether you have a unique closest lattice point, you're guaranteed to have a unique closest lattice point or not. So yeah, there's a like the learning with errors problem, which is sort of the core of lattice-based cryptography, actually it's a distributional BDD problem. That's how you can think about it. It's like sort of where you get a random instance of BDD on some family of lattices, but where alpha is somehow very, very small.
Mhm.
So again, this is sort of like these problems being hard is necessary, but not sufficient for sort of hardness of security of lattice-based crypto.
Thanks.
Right. So just to conclude, so you know, what I talked to you about today was the intersection of lattice-based cryptography and fine-grained complexity. It's a study I'm very excited about. So so far, we've already shown strong runtime lower bounds for key lattice problems, and this is actually an area of research that this is ongoing. So there's work that I didn't talk about by other authors, and also some additional ongoing work that I'm involved in. And yeah, as I said a minute ago, sort of what we have so far is necessary but not sufficient for the security of lattice-based crypto. We've ruled out a variety of attacks on lattice-based crypto, but we haven't gone nearly as far as we'd like. There's a lot more to do. So sort of in the future, we just want to sort of extend this work, you know, in all ways you can imagine. We want to understand there's sort of a smorgasbord of interesting lattice problems. I talked about a couple. They're typically, you know, they're related in sort of a coarse way, but we really want to understand the fine-grained complexity of sort of other lattice problems, especially those that are especially close to the ones used in cryptography. And we also want stronger results where possible. So if we could sort of get strong enough results of this form, it would actually prove unconditionally that our lattice-based cryptography is secure. I mean, this is hopelessly far out of reach right now. It's like much stronger than P is not equal to NP, but still it's something we can work towards and take steps towards, or at least towards understanding. And as I mentioned, you know, just sort of a lot of these complexity results actually followed from geometric questions about lattices, like sort of what lattices look like, and you know, sort of constructing different geometric gadgets related to lattices. So another closely related and interesting direction, which is more just math, is understanding the connections between geometry and complexity. So yeah, that's all. Thanks again for coming.
Thank you.
Thank you.